Oh, geez. Okay. Well, you'll be happy to know I finished page 1 and page 2. So, page 2.5. Okay. Still, for the first day, it's not a bad start. Okay. So, how many of you have studied optimization already in an undergrad class? One. Okay, these are all the dangerous people here. Okay. All right. So this is going to be not as deep as what you studied. Hopefully there's more intuition and more emphasis on the things that are not covered in the textbook, things like modeling and, how do you actually create the mathematical structure in the first place. But that's a trade-off. Unfortunately, there's only guidelines, but there's no actual rules for that. Okay. Anything else? Any other questions about the course or? Okay. All right. We have a few early exits. That's good. I like to have grad course of about 16 people. So half of you are, no, I'm just kidding. I expect this course to be a bit larger than normal. I really feel that the students coming into grad programs don't have enough math. They kind of come in and they've not learned all these different things, and then you're at a big disadvantage when you try to write papers because you have no idea what actually to do. Actually, I should ask one more question. How many people are kind of new students who just started this term over here? Okay, 1, 2. Okay, not too many. Okay. Okay. All right. So next time I'll bring my juggling balls. I promise my students I'll show them how to juggle. So that's the only thing I can do in the break to wake up people. I used to fall asleep in class all the time. It was terrible. I could never stay awake, especially after a lunch class. And I had one of the worst experiences in my life was I was interviewing at a university, and the person who's interviewing me, I was in a seminar class. I had a seminar class. I was in my 5th year at that time, so I didn't really need to take the class, but for some reason I'd convinced myself I wanted to learn parallel compiler architecture or something like, I don't know what it is, something obscure. And there were only 7 people in the class. We sat around the table immediately after lunch, and after 15 minutes I couldn't stay awake. And 7 people around the table. You can see who's sleeping. And he was interviewing me for a job. It was terrible. I hoped he didn't remember me or remember my name. I said, I didn't want to interview with him, but he was there, and I didn't get the job because he probably said, that guy, he slept in every single seminar course, every single class. It was true. I slept in every single class. So my sympathies are with you as a student, but it's still not a good thing to do in class to sleep. So I'll try to keep you awake. On the other hand, he was a really boring lecturer, so a very boring speaker, very, very boring in every respect. So I had good reason to fall asleep, but oh boy, it's terrible. You walk into this room and you see this guy who mostly you've seen through the sleep-induced haze, like, oh, little guy. All right. Now that we're all refreshed, let's start something which is a little bit more fun, and I'm going to actually pretty much follow what I have over here so that I don't can go wrong easily. So what I did over here with this packet on a linked business was to optimize a simple system with just one variable, which was the number of packets you sent, X. So okay, it's kind of simple and easy. Now what I'm going to do is I'm going to drop all pretense that this is not math. I'm going to go straight into a very abstract system of of variables. We just ignore the physical system altogether. I'm going to just throw the equations. Let's not worry about where it comes from, okay? And we'll focus on just how do we optimize it, because you're going to have 2 variables, and then we'll get even more interesting. We'll do 3 variables, and then go into 100,000 variables. So you do 1, 2, 3, and then 100,000. So that's the way it goes. All right. So let's do 2. So here's the system. I'm going to define a system O, which is 2x1 minus x2. So again, just to make sure you're understanding this over here, x1 and x2 are my control parameters. So I have a system with 2 knobs, x1 knob and x2 knob, and the output is a nice simple linear function. It's 2x1 minus x2, and I have the feasibility constraint which says x1 is greater than or equal to 0, x2 is greater than or equal to 0, and the joker in the pack, x1 plus x2 equals 1. Okay, so I don't know why it's like that, but that's what it is. So somehow we have a system where, you know, the two input parameters must add up to 1. Okay, and that's how we define the feasibility. Now what we want to do is to choose the value of x1 and x2 such that O is maximized, because we want to do a maximization rather than minimization. So we want to do maximize O, where O is this, such that these are the constraints. So we have the constraints on the control variables, we have the transfer function written out over here, O in terms of the control variables, the fixed parameter is 2 and the minus 1, and we want to maximize O. That's the mathematical model. So what are you going to do? I'm going to actually show how to do it geometrically, because it's kind of easy to see it that way. So let's just draw this over here. So on the x-axis we'll have x1, that's all possible values of x1, and the y-axis I have x2, all possible values of x2, alright? And what we're going to do is we're going to plot on this basically the allowed values of x1 and x2, alright? So for the first of all, this one says x1 greater than or equal to 0 says that we're in the right half plane over here. So our solution x1, x2, which is some point in this plane, lies over here, and similarly it lies above there, right? Because those are the two parameters. So we can get rid of these two things easily by simply saying the solution lies in this quadrant, okay, of the plane. That's all we know for now. And then we have this one, x1 plus x2 equals 1. That's easy also. We just draw a straight line, and this is basically 1, 0, and this is 0, 1. We draw a line from 1, 0 to 0, 1, and now we know one more thing, which is that not only do we know that x1 plus x2 equals 1 means in this quadrant, we also need to only consider points on this segment between 1, 0 and 0, 1. Okay? So that's, now what we need to do is to find out where on this segment are we going to find the value, where the segment is O maximized. Okay, so how do we do that? Again, it's pretty straightforward. Let's just start at some random point. Let's just pick a point. Okay, let's say I pick a point over here. All right, the value of x1 is 0, the value of x2 is 1. So what's the value of O, which is 2x1 minus x2? It's minus 1. So O equals, all right, okay. So what do? We kind of, let's say we go down over here to some point over here in the middle, okay. And let's just pick some values over here. Let's say this is 0.5, 0.5. We know that's on this line because 0.5 plus 0.5 equals 1. And that's the constraint function. So we know that 0.5, 0.5 is over here. So what's the value of O over here? Okay, O over here is 0.5 because it's 2 times 1 minus 0.5 is 0.5. And then let's just go down over here. What's the value of O over here? Well, I'll just give it to you. It's basically it's 2 because Y is 0. So what we're seeing over here is the following phenomenon. That is that we know that all the solutions lie on this line, okay? They all lie on this line, right? And we can choose some point on this line, and if we move in this direction in the solution space, we find that O increases, okay? In fact, it's very easy to see from the structure of O that O monotonically increases, all right, along this line. As you go further down this line, if you go epsilon, O gets better by, I guess in this case, 3 epsilon, right? You get 2 from here and 1 from here because of some. So you keep going over here until you come over here at this corner point, at this extremal point of the range, we find the maximum value of O, which is 2. Okay, so see what's going on. We find a point. This is a feasible point. This is also a feasible point. These are all feasible points. Okay, we have an infinity of feasible points over here. What is going on is that I find a feasible point, and then I kind of look at a neighbor of the feasible point, and I say, am I better or am I worse? If it's better, fine, let me go there. So I go down an epsilon step, and then I keep going down and say, hey, you know what, this direction looks pretty good to me. If I keep going in this direction, O keeps getting better and better. At some point, I run out of steam. I have no more place to go. I stop over here, and I say, okay, I run out. And this point, which is a corner point, because at this point, essentially, if I go beyond this point, I'm going to go into negative x2 territory, which is prohibited. I find the optimum value of O to be 2. Okay? So, what's going on here? What are the steps? Let's kind of understand the steps. What we do is first, in the geometrical sense, we are depicting the solution space. So the axes are x1, x2, x3, x4, and so on, all the different axes, okay? So each point in this space is a possible solution, okay? It's a possible setting of control variables, all right? Each point is a possible setting. All right. Now, some of these are prohibited. Why are these prohibited? Because the constraints say so. Okay. Anything that's in the lower half on the left is gone by these constraints. So now, what you're doing is you're taking that space and sort of shrinking it down. Okay. We're now shrinking it down to a smaller space, and then what you're finding, based on these constraints, is that portion of the space which is feasible. Okay. This is the feasible. So in our case, the feasibility set defined by the constraints is just a straight line. Okay, then we start at one point over here, just essentially some random point, and we look at the potential. We can look at how should we move to make O bigger, in this because we're maximizing, and we find it says go along the line, and we keep going until we stop. And when we stop, we find the optimal point, which is 1, 0. And again, visually, by inspection, you can see right away that, yeah, obviously, O is maximized when x2 is 0 because that maximizes x1, but you can also see that over here. All right? So the steps that I've shown actually generalize to more than one dimension, more than 2 dimensions. Okay, that's why I wanted to go through it in a little bit more abstract. And I'm going to now do a solution with 3 to show you how that works in 3 dimensions. But in 2 dimensions, it should be clear what's going on. Okay, so before I do that, are there any questions about this over here? Okay, straightforward. Okay, so already you can see how sort of optimization kind of works. So let me now move to the 3-dimension case, 3-variable case, and we have some more interesting structure over here. I'll leave that up just so you can keep it, and I'm going to move on to a different system. So it's a very similar system. We say that O is 3x1 minus x2 minus x3, and similarly x1 plus x2 plus x3 equals 1, and x1, x2, x3 greater than or equal to 0. Okay, and we want to maximize O defined in this way. All right, it's a very, very simple generalization of the previous system. And okay, so now let's try drawing this. So I'll draw that in this fashion. So let me make sure I'm drawing it in the right way. So we have x3 up on top. Then I have, oh, wait a minute, I drew. Okay. Let me just draw it the same way so I'm not going to mess it up. Okay, so again, what we're going to do is define a space where the axes are the control variables x1, x2, x3. So that's what I did over here, very similar to this over here. And now what I want to do is to start figuring out the shape of the space where the solution must lie. Well, these 3 constraints immediately say that my solution lies in the positive octant, right? The 1/8 of the space where all these values are positive. So this is defining the octant, so it lies over here. We can ignore the remaining 7 out of 8, 7/8 of the space as being not very interesting. Now this one over here, x1 plus x2 plus x3 equals 1, just as this defined a line, x1 plus x2 equals 1 defines a line, x1 plus x2 plus x3 equals 1 defines a plane. And what are the coordinates of the plane? Again, that's pretty easy to see. It looks something like this. Try doing that in PowerPoint. Okay, and this value is 1, 0, 0. This one is 0, 1, 0, and this one is 0, 0, 1. All right, so I have these 3 points. Again, because the relationship is linear, we know right away that the edges are lines. We can just draw the lines between the corner points, and we kind of have this over here, right? So we know what? We know that the solution lies somewhere in this shaded plane. Okay, we don't know exactly where it is, but it's somewhere there. Okay, now intuitively, as we saw earlier, we're going to expect it to lie one of the corners. Okay, but we'll prove that in just a second. So how do we start optimizing the system over here? Okay, let's just kind of pick a random point. Let's say I pick this point over here, just like I did over there. So what's the value of O over here? Well, it's 0, 0, 1, and O is this. So the value of O over here is what? Sorry? Minus 1, right? Okay, it's minus 1. And what about the value over here on that corner point? O over here is also going to be minus 1, same thing. Okay, so over here, O was minus 1 at exactly 1 point. Even if you moved epsilon away from it, O was not going to change, it was going to change, right? Here what we find is that O actually is the same on this entire line over here. This entire line over here always has the value minus 1, and why is that? It's because in this line over here, x1 is 0. x1 is 0 because we're on that plane over here, the x1, x2, x3 plane, so x1 is guaranteed to be 0, and x1 is 0, this just becomes x2 plus x3 equals 1, right? The constraint x2 plus x3. So this line is x2 plus x3 equals 1. If x2 plus x3 equals 1, then the function this plus this equals 1, okay? So you just get minus this plus this is just going to be minus 1, because it's going to be minus 1 in the whole thing, right? Because x2 plus x3, so O can be written as 3x1 minus x2 plus x3, and this is going to be 0 minus 1, right? Because x2 plus x3 equals 1, and so we get that O equals minus 1 on the whole line. Just simple math, right? Everybody with me so far? Okay, because of the constraint equation, this combined with this tells me that O is minus 1 on that whole line, no matter where I am. Okay, it's a bit, you should probably go and revise that once more when you go home, because it's easy when I talk to you about it, but you know, you have to really figure it out. Anyway, this is called an isoquant. And iso means same, quant means quantity. It means the quantity, in this case O, is the same along the whole line. It's an isoquant, okay? So what we've done is we've taken the solution space and we found one isoquant. This is the isoquant minus 1. Along this entire line, O stays minus 1. Now what we're going to do is this. We're going to move epsilon in the direction of x1. So what we're going to do is we're going to take the value over here, epsilon on x1. All right? I'm going to erect a plane like this, which is epsilon away, parallel to the x2, x3 plane. I'm going to find the intersection of this plane over here with that plane over there, which is sort of this line like this. And I'm running out of colors over here, so that will have to do for now. Next time I'll bring colored chalk, okay? But this line that I've drawn over here is an epsilon away from the x2, x3 plane and represent the intersection of the epsilon of the plane x1 equals epsilon with the constraint plane x1 plus x2 plus x3 equals 1. All right? So far so good? Okay. Now, what can we say about the value of O over here? Okay? What can we say about the value of O over here? Well, let's think about it. We know that this is going to have, the O is going to have value of 3 epsilon minus x2 plus x3, right? Now x2 plus x3 plus x1 equals 1. x1 is epsilon, so x2 plus x3 equals 1 minus epsilon, right? That's what we have. just from this over here. And if you plug that in over here, we get that O equals 3 epsilon minus 1 minus epsilon, okay, which is equal to 4 epsilon minus 1. Okay? Now, the value of O over there was minus 1, and the value of O over here is 4 epsilon minus 1, which is greater than minus 1. Right? You see what's going on? What I've shown you using just a simple math over here is that if we move an epsilon step away from the x2, x3 plane and we look at the line on the constraint plane, we know that along the entire isoquant, the value of O is 4 epsilon minus 1, and in fact, this value is greater than O equals minus 1. So we've actually gained something. We've jumped from one isoquant to the next isoquant, which is better. Which is just what we wanted to do. We managed to find an isoquant which is better. Imagine that you have a hill, right? You have some hill, and we have these contour lines. Okay, these are the levels which are exactly the same as isoquants. These are the contour lines. I'm over here at minus 1, and I find minus 1 plus 4 epsilon. And I say, hey, that's better, I'm going to go up. What you're doing is sort of climbing a hill 4 epsilon at a time. Okay. Now, I don't recommend you do this in real life. You probably want to take delta steps rather than epsilon steps. But no matter. In this case, by going on epsilon steps over here, what we're doing is we're kind of moving this epsilon plane further and further along the x1 axis. We're going to find better and better values of O. Okay? And they're all isoquants. We don't need to look. If you find even one point, we know that they're all the same because it's isoquant. And these isoquants are parallel to the x2, x3 plane. So we take this plane over here like this and pull it in the x1 direction. So I guess we pull it like this. Okay? As we pull the plane like this, what's going to happen is O is going to get better and better and better 4 epsilon at a time. If you pull it epsilon, it gets 4 epsilon better until finally the plane departs. This plane over here departs from the constraint plane at this point over here. And it departs this plane over here, we find that O equals 3. Again, what we reach is an extremal point of the constraint space. And at that extremal point, as we pull this isoquant plane away from this value over here, we exit with the optimal value. Okay? And that gives you the optimal value of x, or O in this case of being 3 at the point 1, 0, 0. Again, by visual inspection, it's clear that that is indeed the optimal point. You can't get any better than that. And so we found the optimal point over here. Okay? So let me just recap and then I'll pause for questions. What we did was we found the solution space, x1, x2, x3, and essentially every point in this space corresponds to a possible setting of x1, x2, x3, right? They're all just possible settings. Then what we did was we said, okay, let's exclude big chunks of the space, the 7 octants that don't fit this constraint over here. We threw them away, and then we got this octant, and we got this constraint that said, oh, right, everything lies on this plane over here. Then we chose a point over here, and we computed the value of O, something. We looked at another value over here, just to see what it is, and guess what? It's the same thing. Say, oh, great, I found an isoquant. Once you find the isoquant, a little bit of math shows that an epsilon step towards the x1 axis makes it possible for me to find a better isoquant at the 4 epsilon value, okay, or minus 1 plus 4 epsilon value instead of the minus 1 value, and that tells me this is the direction I should pull. And once I start pulling, okay, I'm always going to get better and better because it's a linear system, all right? And when do I stop pulling? I stop pulling when I reach the point where I exit the constraint space. At this point, there's no more space left. I can't go any better, and I exit, okay? And so what I've shown intuitively over here, and I will not show this formally, but I've shown you intuitively over here, is that if we consider this shape over here, this shape which is defined by this and this and this and this plane over here, the extremal value of O lies at one of the vertices. And in fact, one can show that as long as this set of equations is linear, okay, it's a linear system, the optimal value will always lie at one of the vertices. Okay, and this is what's called a polytope. And we're saying that basically the extremal value of the objective function, that is minimal or maximal value, will lie at one of the vertices of the polytope. What we need to do is find the right vertex. Okay, what we need to do actually is to find the isoquant sort of plane, and then pull this plane through, and then it leaves the polytope. It will come out in one of two places. Either it will come out at a point, in which case that's the value, or it can come out parallel to one of the faces, in which case the entire isoquant, all values there are optimal, okay? Or it can come out at a line, okay? It can be like this, and it can come out at a line, then everything along that line, and so on will be the same thing, okay? So we can choose different objective functions, so it emerges as a point, or a line, or a plane, but of course the intuition is the same. It's where the constraint, where the isoquant plane kind of leaves the constrained polytope. Okay? The polytope is just an n dimension, in this case a 3-dimensional solid, and it generalizes to n dimensions. Okay, let me stop here. Are there any questions about this? Any questions about this? Okay, let me see, I want to make sure okay, so now I'm going to kind of jump into, I'm going to give you some intuition about n dimensions, and then we'll probably stop and we'll continue linear programming next time. I think I have enough, I've pumped enough into your head already. So let me tell you what happens when you go into n dimensions. Good things happen and bad things happen. The bad thing that happens is you can't imagine it. Okay, it's very, very hard to imagine. Okay, I have 3 constraints over here. Okay, now I'm going to write x1, x2, x3, x4. All right, I can't draw it. Okay, I can't. I mean, it's already, I'm drawing 3 dimensions in 2. Drawing 4 dimensions in 2 is, it can be done, but it's called a tesseract, but it's not fun to look at. And once we start looking at intersections of these planes, so here I have to draw the intersection. This line represented the intersection of this plane x1 plus x2 plus x3 equals 1 with the plane x1 x1 equals 0, right? Those are the 2 planes, and that's this line over here, this intersection of these 2 planes. So when 2 planes intersect, we get a line. When 2 3-dimensional things intersect, you can get a plane, but when 2 4-dimensional things intersect, you actually get a 3-dimensional thing. Okay, so if you take a 4 cube, a 4 hypercube, and another 4 hypercube, and to intersect these 2 things, the intersection actually is a cube. And it gets worse when you take 2 5-dimensional bodies, intersect them, you get a 4-dimensional body. Okay, so it gets pretty messy to kind of think about these things. So while the geometric intuition serves us, okay, once I say this is a 20-dimensional polytope, actually it's not a 3-dimensional, like an icosahedron or something like that. It's this thing that you cannot imagine, and I cannot imagine. I spent a long time trying to imagine what a 4-dimensional or a 5-dimensional body looks like, and I can't. 4-dimensional, by the way, is easy to imagine. What you imagine is, say, let's see, if you want to imagine a 4-dimensional sphere, this is what it looks like. You look at a sphere that's very small, all right, and then what happens is it grows over time, and then it becomes small again, all right? And the time width, if you will, is the same as the spatial width r. So you define time and space in such a way that you can say 1 second is 1 centimeter, 1 second is 1 meter. If you do that, then if you say 1 second is 1 meter, then the sphere could be of radius 1 meter. And in 1 second, it goes from 0 to a full size 1 meter, and then goes down to 0 again. Okay, that's a 4-dimensional sphere. So each slice, each time slice is a sphere. Right? And the 4th dimension basically means the sphere is growing and shrinking. And it's shrinking and growing exactly at what? Because, basically sine theta. Okay? Because it's in space dimension also, it has the same spherical coordinates. So that's a 4-dimensional sphere. Okay? It's a sphere that grows and shrinks. Now, how's a 5-dimensional sphere? I don't know. It's 5-dimensional sphere is such that, well, I don't know. It's a 4-dimensional sphere when you intersect it with one point in time. So you have to think about this in space. You get the picture. So if you cannot sleep at night, imagine a 5-dimensional sphere. It's wonderful. It puts you to sleep right away. At least it put me to sleep right away. Okay, so I'm going to now try and give you some intuition of how do we do things in 100,000 dimensions. I said there's 2 dimensions, 3 dimensions, let's do 100,000 dimensions. So when you go to 100,000 dimensions, we can forget about geometry altogether. We don't actually have anything. But what we'll do is this. Notice that each vertex over here corresponds to some assignation of the variables x1 equals 0, x2 equals 0, x3 equals 1. Right? So 100,000 dimensions, what we really have is collections of vertices. So we say here's a vertex, x1 equals this, x2 equals this, all the way up to x 100,000 equals something, and that is a vertex of the polytope. All right? So we don't know what it looks like, but this is what one vertex is. We can then take each of these constraints, okay, and say, is this particular point that it shows, is it satisfying the constraint or not? If it's not satisfying the constraint, it's not in the polytope, right? So you want to take this this polytope, and you want to find all the points on it. Okay, like for example, we found all the points in this plane, we shaded it, and the same we want to find this polytope, and we want to find the extremal points on the polytope. And those extremal points where, for example, x1 equals 0 immediately is an extremal point, because we know it's greater than or equal to 0. If it's equal to 0, it must be some vertex, right? So if you have 100,000 variables, just by setting each one to 0, we immediately get some points, right? And so on. So what we end up doing really is to look at a system of equations where these equations over here, x1 plus x3 equals 1, represent constraints on the structure of the polytope. And then what we want to do is we want to find some point on that polytope, and we want to look at the value of O over there. And then we want to find some neighboring points, okay, and some direction to go in. And you say, okay, if you go in this direction, looks like things are getting better. And then we'll move sort of in that point. And what we'll do is we move from point to point to point in this polytope. At the end of it, basically we'll come out to that point, which in the 100,000 dimension space represents pulling the isoquant hyperplane out of the polytope. So just like you put a rabbit out of a hat, you pull the isoquant hyperplane out of this hyperdimensional polytope, and the point where it exits, or the plane where it exits, the hyperplane where it exits, is in fact the optimal point. Okay, so geometry is good to give intuition. We'll do this over here. So next time what I'll do is I'll show you how to kind of go into linear systems, when we just kind of abandon geometry altogether, and how we can start optimizing systems of several 100,000 variables using a simplex approach. Okay, so I'll stop over here. Any questions about this? Okay, great. So it's a short class, and we'll continue next time.